In the moment area method, there are two basic theorems and also two basic things that we can calculate with those theorems. And what we're going to do briefly in this video is talk about the two basic applications and the strategies that emerge out of the application of the moment area theorems. Right, so we can calculate angular deviations. That's the change in angle between two tangents drawn to the curve that turns out to be elastic deflected shape. And we can calculate tangential deviations, which are then how much difference there is between a tangent drawn somewhere else to the elastic deflected curve and then somewhere on the elastic deflected curve. So what you see here represented are two different tangential deviations. The one here at the right at C is the distance between E and C. C is on the elastic deflected shape, and E is just the extension of the tangent way back here that was drawn at A. Hence that's why it's called TC with respect to A. It is the distance between, in this case, point E and point C. TBA, on the other hand, is located over here, rough underneath where the original position B is on the beam, and then you could call the position right here at the elastic deflected shape, that's B prime. And so this tangential deviation is from the tangent, the projection of B down to the tangent, up over to the elastic deflected shape position. That distance, that chord, is between D and B prime. That's called tangential deviation B with respect to A. And what we cleverly do here is if we were interested in the displacement, say, at B, so that would be this little symbol delta that we've got here, little delta B, what we can do is, if we only knew this total height, we could subtract off something we can calculate. That's the tangential deviation B with respect to A. So we can use that then to, what's that total height? Well, that total height can be thought of as being associated with theta A. Now, tangent of theta A is this whole height over this length, so that length is x. Right, so, all right, let's look at that. Tangent of theta A is equal to that total height. That would be from the chord from D to B all over that distance for the triangle, right, opposite over adjacent. That's equal to x. Right, now this is small angle theory, so tangent of theta A is approximately equal to just theta A itself. We often will write it that way. But that means that to get this DB thing and then to subtract off the TBA, that would give us our little delta B. Somehow we now have to find that. And that's where this larger triangle is useful, right? It's another right triangle. We have similar triangles at work here. And so this whole height, this DB business, can be also related to this similarity of that we've got going on here, right? That's equal to x over L times TC with respect to A. And that's how we can go about cleverly figuring out what this displacement is that we actually want. Right? It's a little bit more involved here with the simply supported segment business. It's not as straightforward as it is in the other basic situation that we've got, which is a cantilever or fixed situation, where here when we draw the tangent to the elastic deflected shape way back here at A, well, theta A itself is equal to 0. So the tangent there, the tangent at A, is the same as the original undeflected position of the beam. And that's really handy, right? Because that means that the tangential deviation of any one point is exactly equal to the displacement of that point. So that's why you see here delta B is exactly equal to this tangential deviation of B with respect to A. Now someone has put a little absolute value sign around that because they don't want to worry about what the sign of the calculus of the moment area method is telling us in many cases we can anticipate very clearly what direction this is going to be, and so we can figure out that B moves down, and we can then later on, if we want to indicate a downwards motion with a negative sign, we can add that in later on. Right? So that just gives you the basic essence of how we go about applying the moment area method. These two basic strategies. You have a simply supported system. You want to draw a tangent at one support all the way across to the other, and then figure out what that angle is. And you're like, well, why did you do that? Well, that's established this ratio, or enables us, that's the constant in these two triangles, from which then we can get the shorter distance and subtract off this other little piece. Right? Kind of complicated. Much easier one is the fixed end. So let's go to a numerical example and see how this all works out.